Welcome to Knowledge Share channel. In this video, we will be discussing about some basics of measurements. So why I am posting this video is because in the forthcoming videos, I will be discussing about different types of instruments. Okay, there are many different types of instruments. So we will be discussing about different types of instruments. Only if you are clear with the nomenclature of measurements, then it will be easy for you to understand the working of instruments, because we will be discussing about different types of instruments and we should be knowing the nomenclature in the sense what are the different terminologies that are used in the measurement industry. Okay, as you know that measurements play a very vital role. Because we want to measure most of the quantities, most of the real-time parameters, and it should be very accurate, and it should not be disturbed by the external factors like temperature and other disturbances in the real world scenario. It should have very long life. So these are all there are many qualities for the instruments. And instruments nowadays, there are many scientific research that are going on in instrumentations, many of the instrumentation sector. And there are basically, we can classify these instruments into two types. One is the analog instrument, the other one is the digital instrument. So what is the difference between analog and digital? So you are having a clarity on digital instruments. So digital instruments, it will be displayed with zeros and ones. It will be having, you will be having a digital display will be there as well. LCD displays will be there. So that is what is digital. Even though it is a digital revolution, can we say that all the analog instruments have been replaced with the digital instruments? No. Because in high power applications, even till today, you can see that digital instruments are having certain issues, and because of which the analog instruments are used in most of the high power applications. Okay, maybe in low power applications, digital instruments have taken its market share, but analog instruments have its own market share in the high power instrumentations. Okay. So what do you mean by analog instruments? So in this, we will be discussing about the analog instruments. Okay, so what do you mean by analog instruments? So analog instruments is nothing but, the output will be continuous function of time. The output will be a continuous function of time. For example, you would have used your ammeter, voltmeter and wattmeter, or like frequency meters in your machines lab or somewhere. Okay, so where you will be having some pointer, and that pointer will be deflecting to some value. So if you raise the current, the deflection of the needle will be, the deflection of the pointer will be quite high. If you reduce the value of the voltage or current, then the deflection of the needle or pointer will be less. So this is what the analog meter is all about. So all your instruments that are used in machines lab, and mostly in some of the electronics lab also, they will be using this analog instrumentation, where we will be having a pointer which will be moving over the scale. Okay, pointer which will be moving over the scale. That is an analog instrument. Okay, so as we have already discussed, this particular analog instruments, even nowadays, they are used in high power applications because it is having many advantages compared to the digital instrumentation techniques. Okay. And the basic thing which I want to convey here is, in analog instruments, it is hope you know what is a torque. What is a torque actually? Torque is nothing but force. Okay, it is a force. So which makes this particular needle to move, which makes this particular pointer to move on the scale. It is a force. See, for example, if the magnitude of current is high, then high torque should be produced, so that the pointer will be deflecting to a large value. If low current is passed, then it should deflect to a very small value, and so that the low magnitude is displayed. Is it right? The point is deflected to a very low value. So this is what the concept behind all the analog instrumentations. So here the torque plays a very vital role. Torque. Okay, torque is nothing but the force that is used to move the pointer from the zero deflection to the actual value. That is called as torque. So here, in any analog instrument, there are three types of torque. Okay, there are three types of torque. One is called as a deflection torque. The one is called as a deflecting torque. Okay, I will come to it. So here you can have, okay, there are three types of torque, okay, that is, one is called as the deflecting torque, okay, the next one is called as controlling torque, then third one is called as the damping torque. So what do you mean by deflecting torque? Okay, so three types of torque plays a very vital role in the analog instrumentation. Please understand, this is a very important terminology which is used in on all the analog instruments. Okay, so deflecting torque, controlling torque and damping torque. Deflecting torque, controlling torque and damping torque. So what are the definitions for this deflecting torque? What do you mean by deflecting torque? Deflecting torque is nothing but it is the torque that is required to move the pointer from 0. So from 0, that particular pointer has to move. That is called as deflecting. It has to deflect to 1 from 0. It has to deflect to some other place. That is called as deflecting torque. So what it does is that deflecting torque, it is going to convert the electrical energy to a mechanical force. Okay, that is called as the deflecting torque. Then what do you mean by controlling torque? See, for example, if only deflecting torque is only there, then what is going to happen? Always the pointer will be moving to the last. Is it right? So you will not get the correct value. So that should be a controlling torque. What is it control? It is nothing but opposing force by the instrument, such that the current to be measured produces the deflection which is proportional to the magnitude of the current. Is it clear? So the opposing force in the instrument. So for example, if I am having a spring, okay, normally the example is spring. So I will but that particular pointer will be connected to a spring, and that spring will be acting in the opposite direction with respect to the pointer deflection. Okay, so for example, if the current magnitude is high, then the spring will be deflecting to a very large magnitude. If the current magnitude is less, then the spring will allow only the pointer to deflect or to point to a very less value. So that particular pointer will be connected to a spring, and that spring force is called as a controlling force. So if the control force is absent, then the pointer will be swinging or it will go to the last value. So the control force is normally provided by spring, or in some cases it is given by the gravity, but normally in most of the instrumentation it is used by the spring. Okay, that particular pointer which is deflecting over the scale, will be connected to a spring in order to get the control torque. Then what do you mean by damping torque? So damping torque is nothing but, so here you can see that, for example, see here, okay, in this you can see that, this is my the needle can move. See, this is the actual value. Okay, this theta f is nothing. This theta f is the actual value. This theta f is nothing but the actual value. So here you can see that the needle starts from 0. It goes to the maximum value, and then it is getting reduced and then increased. So you can see. So this is called as underdamped. So this is called as the underdamped. So that is, it is overshooting from the actual value, then reducing, then finally settling to some value. So you could have seen this particular example in many of the lab. You can see that the needle will be deflecting back and forth until it gets settled. So this particular phenomenon is called as underdamped. So this is not a good phenomenon, because this is going to affect your performance of your analog instrument. If underdamping is there, then it means that your device will have a lesser life, or the spring will get damaged easily. So always you should have a good damping, such that the pointer should always rise to this particular value and then settle like this. It should not go beyond the actual value and then coming under and then going up and finally settling. No, that's not that underdamping should never be there. Okay, it should be always avoided. So it should always rise to that particular point smoothly without going to the above the actual steady state value, and then it has to settle like this. So this is called as a steady state value. Is it right? So this is called as the steady state value. So steady state value. So you can see that this is called as a steady state value. Okay. So steady state value. So you can see that this damping can be adjusted. So it can be a critically damped. So there are two types of, either it can be a critically damped or it can be over damped. What do you mean by, so if I give the damping, over damping is there, then it will take more time to settle to the final value. So it should be critically damped. So this is the most highly efficient damping type of damping is nothing but critical damping is the most efficient damping. Critical damping is the most efficient damping, where the pointer goes to the steady state value, okay, within a short period of time, whereas over damping you can see that it takes more time. So this is called as damping. So in order to avoid oscillations, we are using this damping. So you can have to damp out the oscillations. So that is called as damping. Okay. So now again go to the actual this thing. So this is how your so you would have seen many of the instruments, and this is how this instrument look like. So here you can see this is the pointer actually. So this is the pointer. So here I have marked this pointer is there. Okay. So pointer will be over the spindle. Okay, it will be, and here there is a balance weight at the last. So what is the use of this balance weight? This will be providing some damping also. Okay, so this will be connected to a spindle. So this is called a spindle. So spindle will be in vertical direction. Okay, spindle will be in vertical direction and it will be holding the pointer. And this are the control springs. So what is the use of this control spring? So this control spring produces the control torque. So this control spring produces the control torque, which is denoted by TC. Okay, and this what to say, and the magnitude of the current which is flowing through it will be producing the TD. Okay, so pointer will be always encountering the force called as TD, and this TC will make it to settle at a particular value, that is called as controlling torque. And the balance weight or as well, so and the balance weight which is connected to the pointer will be acting as a damping torque. So it will be damping the oscillation. So three types of torque. One is used to deflect the needle. Okay, the other one is used to control to a particular it has to settle at a particular value. Then third one is the damping, which is used to prevent the oscillation. Please understand. Okay, hope you are all clear. So types of damping. So then how to damp? So there are three types of damping. So as I have discussed, there are three types of torques, is it right? One is the deflecting torque, controlling torque and damping torque. Here again, this damping torque plays a very vital role, because as I have said, this damping torque will be executing the efficiency of that particular instrument. Okay, damping torque, because if you have no damping, then it will be oscillating here and there, and because of which the springs and other the other components will worn out easily. So in order to have a better damping and in order to have a better life, we have to choose which type of damping is suitable. So there are three types of damping which is used in any particular instruments. Okay, the first one is air friction damping, the second one is fluid friction damping, the third one is the eddy current damping. Okay, air friction damping uses air, whereas fluid friction damping uses fluid or oil. Eddy current damping, it uses magnet. So when you use magnet, eddy currents will be produced, and that eddy current will be acting in the opposite direction with respect to the it will be settling all the oscillations that are produced by the pointer. Is it clear? So here we will see one by one what is the air friction damping, what is fluid friction damping, and what is eddy current damping. So here this is okay. So here you can see that here I have shown the diagrams for air friction damping. So this is the air friction damping. Okay, so here this one, so this particular part is called as the air friction damping. Okay, which I have marked in violet color. Okay, this is called as the air friction damping. So you can see that in air friction damping, the pointer, you can see it is connected to that particular spindle. Is it right? The pointer is connected to the spindle. Okay, and that spindle again, from this pointer you can see that it is connected to a what is this chamber? So this chamber is there. So this is called as an aluminum chamber is there. An aluminum chamber is there, and in that aluminum chamber you will be having a piston. A piston will be moving, and that will be filled with air. So that is called as air chamber. That is called as air chamber. Okay, that is called as air chamber. So this pointer will be connected to a piston, and that piston will be moving inside this air chamber. Is it clear? And that so that is called as air friction damping. So for example, if the needle is pointing very high, then you can see that this piston also moves along inside the chamber, and because of which the point will be damping at a very fast rate. Okay. Now coming to the next point, that is fluid friction damping. What do you mean by fluid? So this particular thing which I am marking in green, okay, this one is called as a fluid friction damping. Okay, so here you can see that the spindle is placed inside a oil. You can see that the spindle is placed inside an oil. So you know that oil is having some friction. So and because of which, whenever the spindle rotates, so only when the spindle rotates, that particular pointer will move. So, whenever the spindle rotates, it will create this oil will create a friction and it will damp out the oscillations which are produced by the pointer. So, this is this type of damping is called as a fluid friction damping, because I am using oil which is a fluid. Okay. So, it is having a disc which is placed in the oil. That particular spindle will be having a disc which is placed in the oil. Okay. So, hope you are all clear. Okay. That is damping system, 3 types. That is what are that is underdamped, critically damped and overdamped, and similarly there are 3 different type of damping. That is one is the air friction damping, fluid friction damping and eddy current damping. Okay, I will come to eddy current damping. So, in case of air friction damping, we are using an aluminum piston which is attached to the pointer. The pointer moves in the air chamber. The air pressure inside the chamber opposes the oscillations of the pointer. And what is fluid friction damping? It is also similar to the air friction damping. The only difference is air is replaced by the oil. So, the oil is having some viscosity which is greater than air. So, it will be having good damping. So, the disc which is dipped in the oil attached to the pointer, it will be damping the oscillation. So, the final one is nothing but your eddy current damping. Okay. So, it is the best damping. Okay. I will say this particular eddy current damping, I will just mark it in brown color. Okay. So, this particular damping is called as eddy current damping. Eddy current damping. So, we have studied air friction damping, we have studied fluid friction damping, and the third one is eddy current damping. So, this is the best damping. Okay. So, this is the best damping. So, why I am saying best is because it is having best damping. Okay, because the dampings are very fast. So, it behaves according to the Faraday's law and Lenz's law. It has 2 different laws, that is Faraday's law and Lenz's law. So, what is Faraday's law and what is Lenz's law? So, what is Lenz's law actually? See, whenever a conductor moves inside a magnetic field, an EMF is produced. Okay, and this EMF will be opposing the cause producing it. So, what is the cause producing it? It is nothing but the oscillations. So, it will be opposing the oscillations. So, whenever the pointer oscillates, the aluminum disc will also cut the magnetic field. Okay, the aluminum disc will cut the magnetic field, and because of it, so here you can see that whenever this pointer will be oscillating. So, this pointer you can see that whenever it oscillates, so you can see that whenever it is getting, this pointer is oscillating here and there. Okay, when this pointer is oscillating here and there. So, this is attached to the spindle with this aluminum disc. So, this aluminum disc is attached to this is nothing but a circular disc. So, this will be connected to a magnet. So, here you can see that the magnet is there. So, this magnet plays a very vital role. So, since it is this aluminum disc is placed in between the magnet, whenever this aluminum disc rotates, an eddy current will be produced, and that eddy current will always oppose the cause producing this particular oscillation. So, which is nothing but your pointer oscillations, and because of which it will get easily damped. Is it clear? So, this is the best type of damping, because it's the oscillations are damped in a very quick way, as well the life is better. But there is one small drawback in eddy current damping, because it is quite costly, because we are using magnet for damping. So, it is quite costly when compared to the air and fluid friction damping. Okay. But it is more, and also there are some drawbacks which we will be discussing in the upcoming videos, because in some cases this particular eddy current damping may not be suitable. Okay, it will be used only in the PMMC instruments, it is not used in the MI instruments. Anyway, we will be discussing that. Okay. So, really we are coming to the end of the session. I hope that we have discussed about the different types of torques that play a very vital role in any measuring instruments. Okay, and different type of damping. So, as you know that 3 types of torque, one is the deflecting torque, controlling torque, and finally the damping torque. And again, this damping torque, there are 3 types of damping. One is the underdamped, critically damped and overdamped. So, critical damped is the best one. And finally, we have concluded that again, in order to make this damping, we will be having 3 types. There are 3 types of damping. One is called as the air friction damping, fluid friction damping, and third one is called as the eddy current damping. So, eddy current damping is the best one, but it is quite costly. So I'm sure this video has given you good insights. So if you really like this video, please give a like to this video, and as well if you have any doubts you can just comment, and as well if you like to share to some students who will be useful with this video, you can just share it. And if you really like the videos which I post in the channel, subscribe to my channel. Thank you.